My name is Laurent Charlin, and this is joint work with colleagues at Columbia, Rajesh Ranganath, James McInerney, and David Bly. And today I'll talk to you about a novel model for recommendations. So let's look at an example. I care a lot about archive.org. Archive is a preprint server of scientific papers. Every day, thousands of scientists consult it in the search of new and exciting results, right? And if you've never been on the archive, I urge you to go. It's a great website. But here's sort of the screenshot. Here I'm looking at the learning field, or the machine learning field, and it shows paper in chronological order on this Monday, 25th August, 2014. Right? And one interesting thing about the archive for recommendation systems is that it's been around for about 10 years, right? So you can actually look at click data for about 10 years, and you try to understand through this click data how science evolved, and I think that's really exciting. So here's a particular example of a particular paper called the Google Similarity Effect. It sort of came out in 2005, and you see that there was a big hit in 2005, and then people looked at it a little bit over again in 2007, 2008, and there may be a recrudescence here in 2012, right? But what this aims to show is that really the archive is evolving over time. And so in our recommendation systems, we may want to take that into consideration. Particularly, I've shown you that the popularity of papers changes over time, but users' interest also change over time, right? And throughout this talk, I'll use the archives as prototypical example, but I'm sure you all have a data set that you know and love that has these sorts of properties, right? So the theme of this talk is really that recommendations should evolve over time. So let's look at an example of what we could do right now. So imagine you have some click data on the left, some raw data about a paper or about a user. So this is scientists clicking on papers on the archive. You can imagine learning a model, for example, a matrix factorization model, and then visualizing its latent space. So these are the item latent vectors. And this really shows you that this paper is a bit read by people in compressed sensing, it seems like mostly, but also a little bit in data structures and in graphs theory. But this isn't the whole story. I think what you really want is something like this, right? So you want a time-aware model that not only tells you that the popularity of the paper changes over time, but that different people have found this paper useful over time. So here you see that at the beginning, this first spike is really lots of people interested in graph theory, whereas here, around 2009, 2010, then there's a lot more people interested in quantum and computational complexity, right? And once you have a model that gives you this, then it's easy enough to look back at your data and to try to understand what was the event that made people in this other field look at this paper. So what I want to do in this talk is try to understand click data over time. I will look at specifically two tasks of interest. One, let's recommend papers to scientists, and let's take time into account for it. And the other one is, once we fit these models, how do we explore these large quantities of click data to better understand what our data sets are made of? And again, this is motivated by the archive, but it applies in many settings. From a technical point of view, what I will develop is a novel model of user preferences. It's based on a particular type of matrix factorization called Poisson factorization, which we'll go over. And really, what it does is that it allows user and item lane factors to evolve over time. Once we have this model, I'll talk to you a little bit about how we can do inference learning in it. And finally, we'll look at how we can sort of fit data to it, and then understand a little bit about its latent space. So from a sort of graphical point of view, here's what we're going to do. We're first going to posit a model of how the world is generated, and then we're going to come up with learning and inference procedures, and condition on data, we can fit a model, and then do recommendations or explore the latent space of the recommendations to get a better understanding of the data set. Okay, so let's move to some background. Let us recall matrix factorization, specifically Gaussian matrix factorization, which we all know and love. Here's its graphical model. Y here, or shaded nodes, denote absurd variables. You could imagine here that you're trying to model clicks or ratings, that's Y. And what this graphical model says is that user latent factors U and item latent factors V combine in some way to produce or to generate Y's, ratings, right? And in this Gaussian matrix factorization framework, we assume that we'll assume the generative model is completely Gaussian, right? So that is, every distribution is Gaussian. And, you know, if for 1 second you put on your statistician's hat, right, this may be sort of bothersome or troublesome, right? Because really we're trying to model what is mostly discrete data using a continuous distribution, right? So to that effect, there's a paper that appeared this summer at UAI by Prem Gopalan and co-authors that looked at Poisson matrix factorization for recommender systems. The basic idea here is your observations, the Y, are distributed according to a Poisson variable. The rate parameter, or the parameter of this Poisson distribution, is again the dot product between user latent factors and item latent factors. But the user and item latent factors are now distributed according to gammas, which have the positive real domain. And the main idea, which is what these two plots on the bottom show, is that now you're actually modeling discrete data using a discrete distribution, right? And there are many interesting properties of this Poisson factorization. I've highlighted two here that we may care about. One of them is that it works both for the implicit and explicit data case, and that's been showed experimentally. And because of the modeling assumptions that we've made, which I won't go into, this model can be used so inference is very efficient, and thus this model can be used to fit very large, massive data sets. Okay, so that's for sort of the background on matrix factorization, but let us remind ourselves that what we care about in this talk is, things evolving over time. And for this, I introduce dynamic Poisson factorization, or DPF. The main idea behind dynamic Poisson factorization is we'll allow user preferences to evolve over time, and also item popularity to evolve over time. And from a modeling point of view, you can think of this as now assuming that ratings aren't exchangeable over time. Ratings appear at a particular time. Specifically in this model, we'll assume that time is discrete, right? So now instead of having a single observation with no time, you say that you discretize your time into big T bins or time slices. And what this means is basically you take your data set and you just bin it, right? And so what you could do once you've made this sort of modeling choice is that you could say, well, okay, then I'm just going to learn my usual matrix factorization independently for each time step. Of course, you could imagine that this is probably suboptimal, right? Because each matrix factorization will only be allowed to look at sort of a small subset of the data. Rather, what you would like to do is you would like for future time step to be influenced by previous time steps, right? And this is what I show here, where my latent factors, U's and V's, at a particular time step are influenced or are given by the U's and the V's at the previous time step. There are several ways we could do this sort of from a mathematical point of view. We chose one here, which is simple, which is to use a Gaussian time series model, where we say that the latent variable, the latent factors of user n is determined according to a Gaussian with mean of the same latent factor at time t minus 1, right? So this is this link here that we've seen before, right? This 4 links that go to the right. And in addition, and this is important, we have this parameter sigma squared, which really tells us how much evolution or how much difference do we allow in between two time steps, right? So if sigma squared is really high, it means that you allow users to evolve a lot. If sigma squared is small, then you do not allow users to evolve too much, right? And you could learn this in this particular model, or for this particular work, we actually just fixed it, right? And so it's a value you can validate over. Now, if you know or if you remember what I said about Poisson factorization, you'll notice that here there's a bit of an issue because these normal distributions could be negative, but the Poisson rate needs to be non-negative. So what we do instead is a simple trick, which we say the user latent factors and the item latent factors are actually distributed according to a log normal, and that really only means that we're exponentiating them to get positive rates. So that's one innovation. The second innovation is that we'll allow our model to learn things both at a local time varying level and at a global time constant level, right? So I've already talked about local factors, which I highlight here, which are allowed to change over time. In addition, we give the model the capacity to learn about global factors, right? So these are traits that do not change over time, right? And a simple example would be, lately, I've been interested in, for example, deep learning, right? So the local factors would learn that. But globally, I've always been interested in recommender systems and machine learning, for example, right? So the global factors could capture that. And that gives a little bit more flexibility to the model. So now for concreteness, I've drawn a 3-time slice dynamic PF. So we just say there are 3 time slices. This is the full model that we're going to train. Obviously, the number of time slices is a sort of a hyperparameter, which will depend on the data set and other ideas that basically other priors the designer may have. But the one reason why also I'm showing this one is to talk a little bit about inference. So an inference and graphical model, the crux, the problem is to evaluate the posteriors of the latent variables given the observed variables, right? So basically, the distributions of the white nodes given the shaded nodes. And I won't go into too much detail, but basically there are several ways of doing this. You could sort of think of it as, once you have a graphical model, there are tools that will allow you to learn and do inference in this graphical model. I use a generic tool called variational inference. We make a mean field approximation. In this particular model, there's these problems of non-conjugacy, which we can deal with by basically optimizing a looser bound. The details are in the paper. Don't worry too much, it's not too important for the rest of the talk. But what I would like to highlight is that this inference procedure scales linearly with respect to time and linearly with respect to the number of non-zeros, right? So I'm sort of imagining an implicit data setting. And it's actually very easy to parallelize lots of these computations. And so we provide an implementation that does so. Okay, so now that we've looked, I've talked a little bit about the model and I've explained what we've done. Let's have a look at real data and try to see how this model fares on tasks we care about. Let me say that there is lots of related work in this area. Starting from sort of the seminal work of Yehuda Koren for the Netflix prize. One thing we found in this project is that it was difficult to find a method that worked for implicit data and that could scale to the sort of data sets we cared about, right? And so we ended up comparing against this Bayesian tensor probabilistic factorization, BTPF. This is what you'll see in future slides. The experimental setup is as you would imagine. That is, we hold out some part of the data and we try to predict it and see how well we do. But there's an interesting caveat here, which is that really we'd like to see how our model behaves through time, right? So what we'll do is we'll repeat the test procedure for each time step, where at each time step the model is allowed to see all ratings prior, or all observations prior to this time step, and then we test on the subsequent time steps, or it could be multiple subsequent time steps, right? And then all the results I'm going to show are all averages around all the time steps. We care mostly, the model is suitable for explicit and implicit data. In the study though, we restrict ourselves to implicit data, and so we'll look at ranking-based measures, such as NDCG, recalled, mean average rank, and mean reciprocal rank. I won't go into too much detail because I think these are fairly standard. Details are in the paper. So we can have a look at a first data set, a small version of the Netflix data, where we only kept users and items that have sort of a rich history over time, right? And ideally, this is the sort of data set where this sort of model would really shine. So it's 7,000 users, 3,000 items, and 2 million non-zero ratings. And the time slice, which we said each time slice here is 3 months. And we see, and just to be clear, this is actually a setup that was proposed, I think by BTPF, in fact. We see here that compared to BTPF, we do better across these 4 metrics that we look at. And we also do better than PF, and specifically, we've tried 2 versions of PF. One which is allowed to look at all the previous data at a particular time step, and one which is only allowed to train or to look at the previous time step, right? And you can imagine that looking only at the previous time step may be beneficial if user preferences evolve very, very quickly. In this case, it does not seem to be the case. So we also looked at a much larger subset of Netflix, which is 225,000 users and 14,000 items and about 7 million non-zero rating. Again, we binarized the data. Here the time slices were 6 months. And here our BTPF, we could not get it to scale to that size. So we only compare against a static version of PF, so vanilla PF. We see again, the results are pretty consistent with our previous results. And this is a much tougher data set in the sense that we've used many more users that may not have a rich history over time, right? So it's more difficult for our model, which incorporates time to shine, but it still does a little bit better. And finally, a third data set which we really care about, which is the archive data set. This is 10 years of scientists clicking on papers. And the results are, so I should say, I'm sorry, here this is 75,000 users and 5,000 items and 1.3 million clicks. And we sort of hypothesized that scientists evolve at a slower pace than movie watchers, and so we set the time slice to be a little bit longer. And again, the results are very consistent with our previous findings that DPF sort of outperforms these other methods. So now it said there's 2 things we're interested in. This is the first, is recommendation metrics. The second is to try to understand our data set through the latent factors of the model, right? This is what I showed you in one of the first slides. This is now, we can sort of better understand what's going on here, which is these are all the dynamic Poisson factorization factors, both local and global. And we already analyzed this. We can also look at the global factors, and without too much surprise, here it's saying that graph theory is really sort of the main global dominant factor of this paper, which makes sense. Now, I've handpicked in a certain sense this paper. You could ask, what about sort of a random paper you could find? This is a random paper you could find, so it's very much a long tail problem where this paper probably appeared around 2007, 2008, was clicked on a little bit at the beginning or maybe a lot at the beginning. But then not so much after that, right? And so when you sort of browse through these items, this is what you're expecting. But sometimes you see things like this, and you're wondering what's going on here. Especially this peak, right? It seems like lots of people from different subfields were interested in this paper at this time. So then you say, okay, it could be just a problem in the model or a problem in the fitting, maybe. So we could look at this is the sort of the raw click data, but from the raw click data, it seems like these 2 peaks here are reproduced in our model, right? So our model seems to be doing something reasonable. So then the next step is to say, well, okay, what is this paper? And this is the archive paper. This is the author's Perelman, and I'll let you read the title. I didn't know what paper this was. Does anybody know what paper this is? Exactly right. So this is basically one of the papers that solved the Poincaré conjecture, right? And so if you look at this click data, or if you look at the latent variables here, you say, okay, here's a hypothesis of what happened. What happened is the paper was published maybe in 2004, 2005, and then it maybe took a while for people to verify the validity of the proof. And once they did, then there was a huge spike because people were like, wow, we solved this 100-year-old problem, right? And that'd be sort of a good story, but actually if you look at the data, it turns out that this is exactly the time when the author just declined the Fields Medal, right? So basically the author declined the Fields Medal and then everybody started reading his paper. So like, okay, but this is only one data point or one spike, there's a second spike, hopefully something good comes out of this. But if you know the story, this is actually when he rejected the Millennium Prize, right? So somehow even scientists are like gossipy in a sense. So this is 4 items, And now we could talk a little bit about users, so we can do the same sort of analysis and look at users. This particular user started using the archive around 2006 and then used it a lot more in later years. And again, this alone doesn't tell you all that much except how active the user was. But looking at DPF latent factors, you really see that at the beginning, this author had interest for quantum cryptography and graph theory, whereas at the end, he really looked at compressed sensing papers, right? And this is a sort of thing that would be difficult to get at from only log data. Another thing you look at is you could do like fields, like how do fields evolve over time? You can, this figure is in our paper, and you can zoom in and try to understand. I'm just going to highlight two fields here. One, the green one, which is machine learning. You see that according to the archive data, machine learning has been more or less stable, right? Although maybe it's grown a little bit at the beginning. Network analysis seems to have grown a little bit more. So I just wanted to show you that, not only does it do well at recommendations, but it also does well at allowing us to understand these data sets. So if there's one picture you need to remember, I think it's this one, which this model allows us to better understand this data through time and perform recommendations. We've studied implicit data. It works as the model is general enough to work on explicit data as well, and it's scalable. And we do provide source code that you can try out. And in terms of future work, I'll just mention one now, which is continuous time, right? So here we've discretized time. One interesting extension is to say, actually, time should be considered at the minimum possible resolution, maybe a number of seconds or a number of hours, right? And there are sort of various ways you could try to do this modeling. So thank you very much for your attention, and I will take questions.
So we have some time for questions.
Hi, I was wondering how much difference the size of the bins makes, and did you consider continuous time models which would avoid the whole binning issue?
Right, so continuous time is future work, so we have not considered it. There are ways, for example, if you look at the topic model literature, there are dynamic topic models and then there are continuous dynamic topic models, and I think we could do sort of a similar modeling change to allow us to do this. We haven't done so yet. And for your first question, which is about how much time bin makes a difference, we haven't done a rigorous study. I think the three experiments I've showed you were on 3 different time slices, or time slice length. These results seem to be very consistent across the time slice, but we haven't pushed a model, to a single day, for example, or to 5 years. So I'm not exactly sure.
Thanks.
Hi, thanks for the interesting talk. I have actually 2 questions. The first one is relating the fields that you are recognizing on the papers. Do they correspond to the latent factors? And if so, how are you labeling them? How are you recognizing this is machine learning and this is so on?
Yeah, this is a good question. So these fields here, they sort of appear a little bit by magic. And yeah, so basically I looked at the latent factors, and Archive has this nice feature of each categories, or people submit things in categories which are labeled. So based on these labels, I sort of made these. Yeah.
Okay. The second question is relating the results. I noticed that for example, the MRR and the NDCG, they were relatively low. Can you comment a little bit on that? So is it inherently difficult problem that's causing this low evaluation metrics?
Yeah. So the idea here, right, is you need to, well, for example, maybe for Netflix or for Archive, you need to rank roughly 5,000 items, right? And so that's just very difficult. So I think it's a fundamentally difficult task. I guess you could also imagine that there's only revealed preferences, so it's sort of a lower bound on what the true results are. But we have no way, unless you can interact with users and ask them how good the recommendations are, or ask, show them 10 recommendations, really ask them which one they would have clicked on. I don't know of a better way of doing this evaluation.
Okay, thank you.
Yeah, thanks.
Hi, thanks for the great talk. You mentioned that your error has been calculated over all bins and averages it out. Did you try taking the errors, measuring on bin-wise? And there are certain bins that are dominating to this low RMSEs and NDCGs.
Yes. We try, no. The only thing, I mean, these, yes, I have
the reason I ask is that certain users have different taste and that contributes to binning, and then over the time that can, so that's the reason I asked.
Yeah, it's a good question. What we did is look at only the last evaluation, which is what you would do maybe if you wanted to do recommendations today, and the results were very consistent with this. But I don't know how much variation there is in between time slices. That's actually something interesting. I should look at the files. Thanks.
Let me ask one question. So, can this approach be sort of not generalized, but adapted to finding the seminal papers? Meaning that it's nice to sort of figure out, okay, which papers are most sort of clickable, you know, from sort of personalization point of view. But, you know, when I'm on archive, and I'm interested in a certain area, I want the best papers. You know, give me the papers that are really the deepest, the best, sort of, how can we go from this to sort of finding, you know, moving towards finding the, you know, objectively best papers that also fit with my interests?
Yeah, so I think that's a good question. That's a great question. We've thought a little bit about this. We haven't done any sort of follow-up work yet, but we've thought a little bit about this. I think one way of doing it is instead of modeling sort of each user, you maybe just want to see users as being sort of trajectories in latent space, right? And then you could try to build a graph of, you know, a co-occurrence graph between papers and try to figure out which are sort of the nodes or the papers that have lots of incoming edges and maybe some outgoing edges, because these papers sort of reveal a new field of research to people.
Would looking at maybe communities of users instead of individual users be helpful at all? Somehow if you move the level of analysis from like individual users to some kind of research communities and sort of do similar analysis at the more aggregate level, would that try to start getting at maybe sort of the overall best papers, or at least as a proxy? Or
yeah,
I'm just thinking aloud.
Yeah, no. So yes, I do think grouping users somehow is useful. I'm thinking of this archive case. Communities are unobserved, so there's also sort of an inference problem in doing that. And whether or not that helps you to reach the final step, I don't know. But yes, I absolutely agree. This is something I would love to see. This is the paper you must read now, because people that have read it have had these phenomenal ideas. Yeah.
All right.
Thanks.
So this work is a collaboration between the Department of Informatics of the University of Zurich and the British Broadcasting Corporation. The authors are Vivek Powdell and Abram Bernstein from the University of Zurich, and Chris Newell from the BBC. My name is Fabian Christoffel. So what is this talk about? We studied collaborative filtering algorithms for diverse media recommendations, especially of movies, TV shows, and books. And the task that we want to solve is improving the accuracy-diversity trade-off for scalable implementation paradigm. For that, we studied this particular type of algorithms that we call graph vertex ranking algorithms. We tested the performance of these algorithms with a typical item ranking task on 3 different data sets. Our contributions are basically that we combine 3 previous streams of work. One is graph vertex ranking algorithms, recommendation diversity, and random walk sampling. So this approximation procedure that has been introduced in 2004 by Cooper and colleagues. Especially, we introduce a re-ranking procedure of vertex transition probability-based recommendation lists that increase diversity and gives at the same time best-in-class performance of accuracy. We also study the diversity performance of other vertex ranking algorithms as something that hasn't been done before, as far as we know. We also show how we can apply high-performance vertex, the best-performing vertex ranking algorithms to bigger data sets by using this random walk sampling approximation of Cooper and colleagues. So first of all, let's clarify what our notion of diversity is. We simply measure the long-tail item frequency at the top of a recommendation list. So the metric that we use for that is called surprise-led 20 and was introduced by Su et al. In 2010. The mean self-information, surprise is basically the mean self-information of each user's top 20 items. And the self-information of an item decreases for blockbusters item and increases for long-tail items. So why did we choose the term wallflowers in the title of our paper? Wallflowers are, in our understanding, long-tail items that the user likes ranked at the top of a recommendation list. So what is the model that we use? The model is actually pretty simple. We simply use a bipartite user item feedback graph, as it is depicted here on the left-hand side of this figure. Each user and each item is represented by a vertex, and every time when a user accesses an item, so buys books or watches a movie, our graph contains an edge between the user and the item. So with this data model, we can generate a recommendation list by calculating, for instance, random walk transition probabilities. That's what you can see here in this figure. So the small numbers beside the vertices. And especially useful method is calculating the 3-hop transition probabilities. So there is transition probability after random walk of length 3. And that's also what you can see here in this figure. The exact calculation of these transition probabilities are given by the formula in the second figure, which is the inverted degree matrix of the graph multiplied by the adjacency matrix and raised to the power of s. And s is describes the length of the random walks. In the example I just showed you, it would be 3, but it could be also a bigger or a larger odd number, for instance 5 or 7. And this method that I just showed you is called P3 by Cooper and al. And we use the same notation for that. Our data model is basically an implicit, it considers only implicit feedback, so we collect rating values, and our graph doesn't contain, or the edges on our graph doesn't contain any weights, or the graph doesn't contain any parallel edges. Okay, so the method that we introduced, we call it RP3 beta, and it's a popularity-based re-ranking. The goal is, as I already mentioned, that we want to include the long-tail items at the top of a recommendation list, and we basically want to prevent to generate a simply personalized most pop ranking. The idea is very simple. We just normalize the transition probability of P3 by the item popularity. So the exact formula is given here. P3UI is the transition probability from the start user, also for the target user, or for the vertex from the target user to item E. And we divide this transition probability by the degree of the item where the random walk ends, and raise this popularity or the degree of the item to the power of beta. To increase the long tail item frequency at the top of a recommendation list, beta should be positive. If beta would be negative, actually it would increase or we push popular items even further up in the recommendation list. If beta is equal 0, we get the same ranking as with P3. So before I'm going to show you how this re-ranking procedure performs, I shortly introduce you to the methodology that we used. We used 3 different data sets. On one side, we used the medium-sized movie lens data set with 1 million ratings. We used the industry or a real-world data set provided by the BBC, which we call iPlayer dataset. That basically contains the usage behavior of the video on-demand system that the BBC provides, where you basically can watch all the TV shows of the BBC. And we also consider the book crossing dataset, which contains usage statistics of this book sharing platform called Book Crossing. The datasets are quite a bit different in their structure. So, for instance, in the iPlayer dataset, we have many more average ratings per item than per user, while in the book crossing dataset, we see many more, on average, many more ratings per user than per item. The movie lens dataset is a bit more balanced in this way, in this sense. We compared our procedure against 3 different types of baseline algorithms. We considered a couple of other graph vertex ranking algorithms that have been previously introduced. And we also considered 3 more standard approaches. So on one side, 2K, AK nearest neighbor procedures with cosine similarity, and a matrix factorization procedure, which is called PPRMF, introduced by Randall and colleagues in 2009. To facilitate comparison, we also included perfect recommender, which basically is basically a virtual recommender that ranks all the hits of a target user at the top of the recommendation list. Of course, we also calculated the unpersonalized most pop ranking, and a random recommender. So generate a random recommendation list for each user. The task that we used to test our procedure and these baseline algorithms is a simple item ranking task. So we just rank all the items in the user's test set according to decreasing popularity or decreasing user preference. Okay. So what is the performance that we can achieve with our RP3 re-ranking procedure? First, I'm going to show you how we perform in terms of accuracy measured by area under the curve. And you can see basically that RP3 beta gives best or second best performance for all the 3 data sets. And also quite interesting is that if you compare the RP3 beta ranking to the ranking of P3, so the original ranking, which is the green bar, and our method is the red bar, we see that we could achieve an improvement for, in terms of AUC accuracy for all 3 data sets. Other quite well-performing vertex ranking algorithms are H lambda. That is the best performing vertex ranking algorithm, or overall best performing ranking algorithm for the iPlay dataset and book crossing, and second best for movie lens, and also quite good performing vertex ranking algorithm is P3 alpha, which is third best for all 3 data sets in terms of accuracy. We also considered the performance by precision at 20. So we simply counted the number of hits in a user's test set among the top 20 items, and we see here a very similar picture. RP3 beta also is among the best performing algorithm, so it's the best performing algorithm for movie lens M, and second best for iPlayer. However, it doesn't perform as well on the book crossing data. We also see that we could also find a clear improvement in terms of precision between P3, so the original ranking, and RP3 beta. Also again, we find that H lambda gives pretty good rankings for all 3 data sets, especially it performs also well in the book crossing case. Now, in our study, we weren't just interested how good we are in terms of accuracy, achieving accuracy, but we also wanted to improve diversity measured by this long tail item frequency at the top of the recommendation list. And here we see that our vertex re-ranking procedure actually fulfills the intended goal. So for all 3 data sets, we could improve the diversity measured by surprisal at 20. And again, we find that RP3 beta is better than P3. Again, the 3 best performing vertex ranking algorithms are RP3 beta, H lambda, and P3 alpha. With one exception, which is this L plus algorithm, which gives like the overall best performance in terms of diversity for book crossing. But we have to keep in mind that this L plus algorithm is actually quite unprecise. So it seems that L plus actually does a good job in putting long tail items at the top of the recommendation list, but these recommendations are very liked by the users. Okay. So now we found that RP3 beta is a procedure that gives quite good accuracy and diversity performance, but we also wanted to find a way to implement this method in a scalable way. And for that we used this random walk sampling procedure that was or random walk sampling approach that was introduced by Cooper in 2004. So we found then an algorithm that could not only be applied to our RP3 beta re-ranking procedure, but also to P3 alpha and H lambda, so the two other quite good performing vertex ranking algorithms. And the procedure is actually very simple. For a given target user, we start with a random walk at a given target user and simply take a random neighbor of this user and repeat this procedure 3 times. So hop from one vertex to the other and store the intermediate degrees of the degree of the intermediate vertices. And then what we do, we calculate this CRW coefficient, which differs for all the 3 different vertex ranking algorithms. And that's the only difference that between the 3 algorithms to get the approximation of the original ranking. So then we repeat this sampling procedure several times until we reach convergency, basically until the recommendation list doesn't change anymore. And besides the improved scalability that was proposed by Cooper et al. In 2004, this algorithm has also a nice property of being an anytime algorithm. So we can basically abort calculation at any time and still generate a recommendation list, and we don't have to wait until our calculation reaches the exact ranking at the end. But of course under the cost of reduced accuracy. Okay. So now how does this ranking or random walk sampling approximations perform against the original, the exact calculations? So here we plotted for each of the 3 random walk sampling approximation method the performance in terms of, again, precision, AUC and precision at 20, but also diversity. And you can also see, that on the right-hand side of each subplot, you find that the performance of the exact calculation is indicated with the small labels, and you basically see that after if we draw a sample that's big enough, so let's say for instance 10 million random walks, we basically end up at the same ranking, or we achieve the same performance and the same recommendation performance, independent whether we use the sampling approximation or the exact calculation. So this basically means that our sampling approximation gives the exact same ranking in the end as the exact calculation. What's also quite interesting in this plot is actually the different convergence rate of the 3 different sampling approximation procedures. For instance, if we consider the movie lens M dataset, you see that P3 alpha converges quite a bit or much quicker to the performance of the exact calculation than the other 2 algorithms. So this basically could indicate that if we want to generate recommendations in an environment with limited computational resources, it's probably better to use P3 alpha than RP3 beta and H lambda, because we already get a better, especially accuracy at lower after drawing or after a shorter simulation time, so to say. If we consider the iPlay dataset here, it's quite clear that RP3 beta would be chosen in any case because it gives almost the same accuracy, slightly worse surprisal value, but quite good accuracy, and it has a nice advantage of converging quicker. So actually, we get better performance for lower computational costs. For the book crossing case, it's not really clear, or we would probably choose H lambda if we have like sufficient computational resources, because it gets quite good surprisal values, but clearly better precision than RP3 beta. In terms of limited computational resources, it's not really clear what we should choose here. Okay, short conclusion of our work. So we introduced a popularity-based re-ranking procedure based on random walk transition probabilities that we call RP3 beta. We found that with RP3 beta we can increase recommendation accuracy, and at the same time we can increase the long tail item frequency, so the diversity, or our diversity measure, at the top of the recommendation list. Again, you see in this in the figures how the difference between the original rankings of P3 and RP3 beta. It's a clear improvement in both cases for the Moodlens M dataset. Besides that, we introduced vertex ranking algorithms for the best. We introduced random walk sampling procedures for the best performing vertex ranking algorithms, P3 alpha, RP3 beta, and H lambda. And we showed that this this random walk sampling approximation converges to the performance of the exact calculations. But to decide which sampling algorithm would be the best in a given environment, we would need to consider on one side the available computational resources, but also the dataset structure probably. So what are future works that we want to do? We would like to see if these wallflowers that we introduced at the top of the recommendation list, so these long tail items, are perceived by the user really as good recommendations. So we would like to do a user study for that. Then we would also like to explain, or I would like to find out how we can explain this difference in convergence rate between the three different random walk sampling algorithms that we introduced. And we would also like to measure the difference in runtime performances for the three different sampling procedures. Okay, short acknowledgement of my work. I would like to thank all the members of the Dynamic and Distributed Information System Group of the University of Zurich. I'm very grateful to the staff at BBC R&D for providing us this real-world dataset from their iPlayer video-on-demand system and for hosting me in their lab as an intern. I would like to thank the organizers of the conference for giving me the possibility to present my work here. We got some financial support from the BBC and Health Foundation. We are really grateful for that, and would like to thank you for attending my talk.
So we have time for questions. Yeah, let me start maybe with a simple question, and perhaps you'll mention this a little bit. It's always nice when the techniques are parameterizable in terms of how heavy the long tail item presence is in your top N list. So is there an easy way to sort of parameterize, maybe have certain parameters that basically allows users to, on a, say, personal, individual level, adjust
the long tail item frequency?
Yes.
Yeah, that's basically this beta parameter.
Okay.
So if we increase beta, the frequency of long tail items get increased. Yeah.
And sort of a follow-up question is, the diversity in this paper is operationalized by long tail items, right? There are lots of different diversity definitions in the literature. Some of them are related to long tail, but not all of them. Some of them basically just looking at are the items that are being recommended in your top N list are different enough in terms of content features and stuff. And they may still be popular items. So in this sense, have you tried some alternative diversity measures and sort of...
We didn't consider any features based on the content of the items, but we considered also how's it called? In the paper, we also described two other diversity matrices, which are which basically measure how similar recommendation list among each user on one side, and then also we introduced the metric, or we used the metric that simply awards the overall spread of recommendations. So, which basically increases if all the items in a corpus are recommended. That's these two additional metrics that we used. But we haven't considered like whether we only recommend science fiction movies or only action movies.
Hi, it's more maybe a comment than a question. I also wonder if you're aware of the paper item popularity and recommendation accuracy. at RecSys 2011, because that basically had a very similar idea that you have also this exponent beta.
No, what was the title of the paper?
It's called Item Popularity and Recommendation Accuracy. So what the idea of this paper is, it uses matrix factorization, and then it introduces a weight for the least squares when it optimizes it. And the weight is basically a function of the popularity to the exponent of beta, which has basically the same effect. So with changing beta, you can have more or less of the long tail items being at the top of the recommendation. It also has a little user study that shows that going a little bit to the long tail is preferred by the users, but not going too much to the long tail. So it could be useful maybe also for your future work to look at that paper.
Yeah, probably should look into that then.
I want to go back to the first question, actually. So why do you want to have long tail items in your top end at all? I mean, they won't be sold, so it isn't better to find some other way of categorizing diversity? Because long tail items, well, I can understand that you want to do good recommendations, product recommendations for long tail items. But I don't think I would like to have long tail items in my top end list, because they will not be sold, right?
Yeah. I don't know. I mean, if you really like, for instance, documentaries, and if there is a really nice new documentary that has nobody watched yet, it might be still interesting for you, even though it's from the same group of items, right? That has, for instance, a similar genre. So in this case, like diversity metric that measures the diversity based on item features would give very low scores. But I mean, it could be still interesting for a user, I would say.
Yeah, but that means that you look at frequencies rather than total purchases, which makes the problem go back to having more popular products or items. So there should be a reason for putting the long tail items there. That's my comment, really.
Okay. Thank you very much. Thanks.
So morning everyone, it's a great honor to have you attend this talk. I'm Ziki Liu from Xi'an Jiaotong University and also a visiting student at Carnegie Mellon University. This is a joint work with my collaborator Yuxiang Wang and advisor Alex Mola. So this is another talk on differential privacy, but maybe we focus on how to make the algorithm scalable, how to make it fast. So we will first begin with the recent observation that the Bayesian posterior sampling from a bounded likelihood, log likelihood preserve full B differential privacy. Here, where the B is the bound of the likelihood, it means that if we want to design a differentially private machine learning algorithm, we don't need to custom design a new statistical model. We just retrofit an existing one. Secondly, we will talk about differential privacy in matrix factorization. We introduce different kind of bound and how to design different level of privacy, and a additional bonus is how to make personalized differential privacy. And at the final, we talk about how to boost the performance, which is cheap and fast. So your user-generated data nowadays has been increased exponentially, and personal information has been collected and analyzed by governments, companies and research centers like our here at Netflix, Booking.com, Amazon, Xing, and so on. So it's great important to protect your users' privacy nowadays. A famous example is linkage attack. In 2008, Nero, Yanan, and Shimatikov, they exploit IMDb data to de-anonymize the users from Netflix data. It tells us that even we anonymize our users in the data set, we can't guarantee the privacy. It comes to differential privacy. Actually, we have a great talk yesterday, and here I just gave a simple concept about it. So the chance that noisy release results is nearly the same given any data word data, which the two data, any of the two data, the Hamming distance between them is 1. So if given R, the release result R, we cannot infer which possible word data it comes from. So in our scenario, the word data can be the user. So in this case, we can actually use differential privacy to prevent any kind of linkage attack. So, but why isn't differential privacy used in practice then? Basically is because the gap between theory and practice. Usually we derive a very large constant, so it's not very practical And also, in most cases, we need additional implementation and lots of engineering efforts, and we also need to have a huge parameter training. This comes to why we need to make it fast. So, a recent work from Wang, Feinberg, and Smola, they claim that Bayesian posterior sampling with bounded log likelihood is differentially private for free. It means if you can guarantee the sampling, you are sampling from the exact distribution, one released sample can preserve for B differential privacy, where B is a bound of the log likelihood. In this paper, we are also endorsing the recent Bayesian optimization, stochastic gradient descent, gradient MC, especially SGLD as stochastic gradient Lagrange dynamics to boost our algorithm. A recap of matrix factorization from a Bayesian wheel. We want to estimate a distribution or maximize the posterior of the latent user factor, and the joint latent item factor given the rating data R and some hyperparameters. Usually we model the ratings as a Gaussian with inner product as a mean. Also as some priors on the U and V. Also usually we assume they are Gaussian because of the conjugate prior. And yeah, so we can, if we set the precision parameter a single value, we can get a very familiar least mean square object as follows. As we said, if the log likelihood is bound, and when we sampling from the posterior distribution, we can preserve the differential privacy for free. So it comes to the how to bound your algorithm. It depends on your requirement. If you need to protect your ratings, users the ratings, you may need to need rating level privacy, which means any malicious users can infer any user's opinion on any movie. This is we can bound the loss of a single rating. For user level privacy, which is exponentially stronger than rating level privacy, it means that any malicious users cannot infer any user's opinions on all the movies. That is, we can't infer if a user is in the database or not. So it's very effective to prevent the linkage attack problem. But the bound is obviously larger than rating level privacy. You need to bound the sum of the loss of one user's all the ratings. So next is it bounded? Of course it's bounded. Obviously the ratings are usually fixed, and the estimates usually you need to make the estimates stay out of you usually don't want to your estimates stay outside of your rating span because it's the larger loss function, right? So it's bounded, but it's still very large. It's still a very large bound because for some users they have a very huge number of ratings. In this case, we have two tries. First is trimming. Obviously, because of the power law distribution, only a tiny number of users they have a very huge number of ratings, so it's still reasonable to have a threshold to cut them off. And also we can reweight our loss function for each user in this case, which means if one user have a lot of ratings, we can have a small weight for them. The additional bonus is that it can calibrate the privacy protection for each user independently, which is personalized privacy. Which formally, if we set WI for user I such that he have a bound BI, here the tau is trimming threshold, and MI is user I's amount of ratings, then our algorithm can guarantee this personalized differential privacy for user I. So now our objective is to sample from this distribution. If we set if0 equals to 4b, actually we are sampling from the original distribution, which naturally guarantee 4b differential privacy. And if we set if0 smaller than 4b, we are actually sampling from a flatter distribution. So it increases the degree of the differential privacy. Now we're talking about how to boost our algorithm. So it's simple 3 components. We first read, update, and write. A lot of efforts on how to read data in really large scale data scenario, and because we implement our algorithm in a single machine, so we maintain our state in the local as a local state. The challenge is, if we look at our update operations, this is SGD updates. So every time we need to read the parameters of U, latent parameters U, and latent factor and V. So, and we also need to write them. So, this is a benchmark on a 2011 MacBook Pro. Basically, if you see this table, it can be seen that level 1 cache bandwidth is an order faster than RAM bandwidth. So our idea is to make our data flow on a cache level. So as for Netflix data, as an example, we have 100 million ratings, 2,000 dimensions if we set it, and 15 iterations to converge. Given each rating, we need 6 reads and 3 writes per update. It's 200 terabytes I/O. The runtime should be very large, and mainly it consists of RAM latency and RAM bandwidth. We deal with RAM latency by pipeline design. The basic idea is if we want that data, we don't request it right now. We prefetch the data before in advance, and the RAM for the RAM bandwidth, we actually push the data flow on a cache level. So we can finally get a 560 seconds for a 2,000 dimension Netflix data. The basic idea is, according to the Power law, there are tiny popular movies that computes most of the ratings. So actually we can cache them, all of them in the cache, and for last of them, which are infrequent, we can prefetch them. And for latent user factors, we actually read per user for each core. And in this case, for each iteration, we only have 1 cache miss for each user, and some very low-level system optimizations, like how to avoid different CPU to write the same cache line. This is the table is a result from a profiler cache grant compiled with our algorithm cache efficient SGD and GraphQi on a single machine. This across different dimensions, 16, 200, 2000, and it shows that our algorithm is very cache efficient compared with GraphQi, and this explains why our algorithm can have a big around 3 times speed up than GraphQi. So the left figure is Netflix data, and the right figure is Yahoo Music, which have 250 million ratings. And we compiled our cache efficient SGD algorithm, the fast SGLD implementation. That is actually the differential private algorithm. And GraphQi, GraphLab, and Bitmark. Bitmark is the GPU framework implementation. It's distributed. We run it on a G2.8X large, which have 4 GPUs, and with each GPU have 4 gigabytes memory. And yeah, actually, even our differentially private algorithm, fast SGLD, can comparable with GraphQi, even better. And BinMax seems doesn't scale well, especially to 2000 dimensions. This may be because there are too many time consuming between the memory from CPU to GPU. The convergence, this is the result on Yahoo Music data on dimension 2048. Actually, our algorithm converge very quickly. And some more trick about algorithm. For example, for SGLD, stochastic gradient large range dynamics, no matter how you set your mini batch, 1 or 100 or what, for each update, you need to add a Gaussian to the whole parameter space. So this is quite expensive if you have a large matrix U and large matrix V. So we bookkeeping the counts that the Gaussian should be added to each entry. This is actually very, very similar to SGD implementation, but and without actual cost, but implement the exact algorithm. And it's very efficient and order faster than some existing, even distributed version. So also the Gaussian random variables, the generating the process is very slow in our code. So we actually pre-generate the table and use a random offset with bug reads. So it's also cache efficient in our implementation. And this is guide for how to generate how large size you need to generate a Gaussian table in advance. Actually, very surprisingly, only a 10 to 4 large Gaussian tables on a Yahoo Music data, where we set the dimensions as 16 can work very well. And according to the two-sample test, our scheme actually can serially approximate the IID, Gaussian random variables. So at last, I will show the accuracy of user-level differential privacy when we change the privacy budget. So the axis is the privacy budget. We set it's set from 0.25 to 2,500. Actually, this is on the results on the Netflix data, and actually it's okay. We can have okay accuracy when we set the budget IP0 as 2.5, and we still can guarantee some okay, good differential privacy. To explain this figure as a rating level differential privacy, we just divide the axis IP0 by 200. So for a rating level privacy, actually our algorithm can can get a very well accuracy and have a very strong guarantee about the privacy loss. To summary and take away, our work is so for anyone who want to design differentially private machine learning algorithm, it's simple. It's just a sample from a scale distribution. That's it. And we describe how we boost our algorithm, especially for matrix factorization using SGD and SGLD style algorithm. and we accomplish the 3 goals: accuracy, speed, and privacy. Our code is available at dmlc@github.com. For those who are unknown about DMLC, I will encourage you to have a visit, pay a visit there, if you are interested in dealing with very large-scale data site. And a distribution, we also work out a distributed version with Mu, which can handle billions of data with billions of features. This is, to our best knowledge, this is currently the biggest, the largest, the most scalable factorization machine. Thank you.
So questions? So maybe I'll start then. And maybe it's more of a comment, sort of philosophical comment than a question, but it seems like, I mean, we all know that there is inherent trade-off between personalization and privacy, and it seems like the differential privacy is helpful, the most helpful to those users who need recommender systems the least. In a sense that if I have very mainstream preferences, I look like everyone else. I like, you know, all the blockbusters and everything. It's very easy to hide me in the data set. But if I have very unique preferences that, you know, I'm really standing out from the crowd, I mean, I would really benefit from a recommender system to try me, you know, like find something niche that I know I like, and I'm alone in that, right? But now it might be very difficult to hide a person like that, you know, in a data set. And so my question is, have you tried to look at accuracy, privacy sort of trade-off, maybe for like the extreme, let's say 5%, or 10, not across, you know, RMSE, let's say entire population, but, you know, here is for the most difficult 5% of the users. Because clearly, I definitely agree that for maybe 50%, 60%, 80% of the users, you can probably hide them really well.
Yeah.
So the question is sort of, you know, what do you think about sort of that whole trade-off, and have you tried to look at like the extreme, you know, like the most different set of users, and, you know, would be interesting to see some analysis sort of specifically tailored to that.
Okay, it's a great question, and actually you can think the personalized differential privacy in 2 aspects. One way is you can do for users, and one way you can do for items. For those users, they can set their some sensitive about the differential privacy. About for example, some users would like to have it's very open, and but some users may would like to protect his or her privacy, and also from a aspect of movies. So, for example, if one user he watched Titanic, which is a fantastic movie, he don't need to protect something. But if he or her watch something bad, so yeah, in this case, maybe he would like to protect that kind of movies. So, but I think this is a very promising direction to work on. Currently, we haven't have some results about such direction. So, but we will work on. So, yeah, thank you.
This is, I guess, a follow-up question, and also sort of related to yesterday's talk. So I think in yesterday's talk, the presenter maybe responding to a question said that the epsilon is really sort of not intuitive, right? And so I think if you were to let users decide what their privacy level is, that would be one thing you would need to communicate with them, right? So what does it mean to be more or less private in practice? Is there any work, or do you have any ideas about how to go about this? Either sort of interpreting the epsilon value, either telling something else to the user that would sort of make sense, and then the user could sort of tell you, okay, you know, I care about this, but not to this point, or I'm okay if people know I watched Titanic, but not okay if they know I watched this other movie that is more private.
Sorry, can you, I can't understand, can you repeat?
The whole thing, or is there a part that, yeah, so I guess the idea is, how do you communicate to the user what epsilon means?
What?
How do you communicate to the user what epsilon means?
Oh.
Or is there a way? I mean, that's an open question.
mean-
There may not be an answer.
You mean this
Yes, yeah.
one? Okay.
Is there a way?
There is actually a definition about differential privacy at the first slide. So for any two different data sets where the Hamming distance is 1, so only one record is different, and they are bounded by this epsilon.
Yeah, I
So
understand, but
yeah.
I guess I'm wondering, like, how could I explain this to my mother?
So if actually in most time, if epsilon, if epsilon is smaller than 1, we can say it's a strong guarantee about the differential privacy. Yeah.
Those are good.
So, but in this case, because the user level differential privacy is very difficult than the rating level privacy. So it's, but I think the 2.5, this point is also a okay result for those systems to want to have a user level, which is very strong because it can prevent the linkage attack. Yeah.
Yeah, I think the question though was that, you know, how do you explain it to everyday users? If you, for example, just, you know, you log into Netflix and there is some kind of a menu and say, how private do you want to be? Like, how do you explain what epsilon is to somebody's grandmother, let's say, you know, sort of, how do you choose it? So I don't know if there's maybe possibility to do some kind of user studies and see how users, you know, whether they truly understand sort of what they're choosing and how to.
Yeah, but because the user may have no intuition how to set the epsilon, so maybe, we can do some supervised learning, like we first collect some data that the user is suitable with the privacy budget they set, and yeah.
Maybe time for one last question.
You just stated that setting the epsilon to be 2.5 can prevent the linkage attack.
Yeah.
Can you show some proof for that? Is it in the paper?
Yeah, you can have a look at the detail of the paper.
That's proof, okay?
Or you can talk with me later, or.
Okay, all right.